meters above the ground, 546 meters from the north side, and 1,914 meters from the southern end. There was no room for error. The only chance they had to get it right was with GPS, accurate to within 4 millimeters. Using signals from multiple satellites, the team could pinpoint their position and make sure they're on target for that critical point in the sky they needed to hit. Month after month, the piers climbed higher. Finally, by November 2003, they reached their full height. At 245 meters, Pier 2 becomes the highest bridge pier in the world. But is this record-breaking pillar where it's supposed to be? Amazingly, it's dead on target to within 2 centimeters. Champagne corks pop. It's time for a major celebration. Against all the odds, they were 1 month ahead of schedule, but the team couldn't afford to relax. The next stage of the project would be the most difficult part of the build. Phase 2 of building the world's tallest bridge involved putting a 2.5-kilometer roadway weighing 36,000 tons on top of the piers, a full 270 meters above the River Tarn. Bridge builders know danger comes with the territory, but working at these heights can be lethal. More than 34 died constructing New York's Brooklyn Bridge. 35 died in 1970 on the Westgate Bridge in Melbourne, Australia. And 1 year later, 13 workers were killed when the Koblenz Bridge in Germany collapsed into the Rhine. With these fatalities in mind, the team decided to fabricate the entire road deck on the safety of solid ground. This meant building it in steel, which in theory would be much safer than lifting vast concrete sections hundreds of meters into position. There's only one problem with this plan. No one had ever put a road deck on piers anything like this height before, let alone over a 2.5-kilometer span. In the end, only one steel manufacturer had the courage to take on this colossal challenge. Eiffel, the steel firm set up by the great French engineer. Eiffel built what was once the tallest bridge in the world, the Garrabee Viaduct in southern France, before getting round to the framing for New York's Statue of Liberty and, of course, his signature tower in Paris. But despite the company's experience, Eiffel's director, Marc Buonanno, knew he was taking a serious risk.
It was a gamble for the company, because if there had been a mistake, if it hadn't worked, it would have been the whole company.
They fabricated the massive sections that would make up the road deck in the company's steel factories. This immense jigsaw puzzle involved manufacturing 2,200 separate sections, weighing up to 90 tons, and some of them 22 meters long. Their accuracy is measured with a laser to within a fraction of a millimeter. The huge square tubes are the central spine that should make the deck rigid. The triangular side panels will be welded on either side to create the width for a 4-lane highway. To meet the punishing schedule, Buonanno automated the manufacturing with a 2-headed welding robot and a plasma cutting machine. Each cutting pattern or template is programmed into the computer. Then the machine automatically blazes its way through the steel. The torch reaches a scorching 28,000 degrees centigrade. That's 5 times the temperature of the Earth's inner core. But cutting and welding was the easy part. The hard part was getting these monster sections the hundreds of kilometers from the factories to Millau. The routes had to be planned with precision to avoid major damage. The police coordinated safety and clearances. Even with that level of preparation, some obstacles felt as if they're cutting it just too close for comfort. And this was no one-off event. To build the viaduct took over 2,000 of these extraordinary road convoys. The components arrived at assembly plants set up, one on either side of the valley. Here, the pieces of the massive jigsaw puzzle were welded together to form the two halves of the deck. But getting these two halves to span the valley on top of the world's tallest bridge piers would be a major challenge. They'd be the first team to put a road deck on a pier taller than an 80-story skyscraper. And pushing bridge building beyond anything attempted before, they planned to slide the entire 2.5-kilometer road deck over in two colossal pieces. The bridge's chief engineer, Jean-Marie Kremer, was one of the few people who believed it could be done.
All the engineers who know this method, who were in the know, didn't believe it was possible.
If the team had got their calculations wrong, the entire structure could collapse into the valley.
We found a solution for the construction, which was to launch the bridge from the two sides. One part on the Larzac Plateau, one on the Rouge Plateau. And to push them from the two sides and to make them come and meet here above the River Tarn.
Smaller bridges use a similar technique. A powerful set of hydraulic rams literally pumps the deck from one side to the other. But Millau would be the longest launch ever attempted over the highest piers in the world, and the results could spell disaster. The deck is so slender, it would bend and collapse if it were pushed out over the 342-meter spans between each pier. The furthest anyone's previously managed is less than half that distance. The first part of the solution was simple. Fit a pylon so its cables support the front of the deck as it goes out over the valley. Then construct temporary steel support towers that halve the spans to a more manageable 171 meters. These steel towers were a construction feat in themselves. The largest, over 170 meters high, is the tallest ever built, and they needed to carry a massive load. 7,000 tons as the leading edge of the deck, together with the first 90-meter pylon slide over. And simply pushing this enormous weight over the top of the vulnerable piers would bring them crashing to the ground. This was the nightmare scenario.
If we'd done a conventional launch, we would have knocked the piers over like the pins in a bowling alley.
Someone needed to reinvent the way this type of bridge is built. And it's Marc Buonamo with Jean-Marie Kremer who came up with the breakthrough. The basic principle can be demonstrated with a heavy box and a wobbly table.
With a normal launch, you knock over the piers. I want to advance the deck over the pier, but if I push the deck from here, I'd knock over the piers, because they're so tall. The idea is to install a launching system on top of the pier, and that way, if I push the deck, it has no effect on the stability of the piers, and the piers won't fall over.
The trick is to use a series of these launching systems to jack up the deck and inch it forward.